Hi everyone, this is Julie. I hope you can hear me. Welcome to today's first session of the Great Data Cleanup Campaign for the summer 2020. We'll get started in just a minute. Thanks. Hi everyone, welcome to today's short online seminar on what is data management. As a note, this session is being recorded and you will receive a notification when the recording and the slides are available. If you have any questions at any time throughout today's presentation, please enter them into the chat and I will try to answer them at the end of today's session. So again, I'm Julie Goldman, the Research Data Services Librarian at Countway Library. I offer a lot of these data management training classes, but I'm also available for consultations on identifying best practices, creating a data management plan, or finding data. So feel free to reach out to me if you have any questions on these topics. I also co-chair the LMA Research Data Management Working Group. And this working group includes members of the entire Longwood Medical Area community from many areas such as the library, information technology, research computing, research cores, and affiliate hospitals. And we maintain this website, which is full of resources and information. So we really suggest that you bookmark this website and reference it as needed. So let's review today's learning objectives. We'll learn about research data management. We'll understand why data management is important. We'll explore how data management applies to you and your research area. And you'll receive resources and contacts for future help. So in this session, we are really going to focus on the role of data management in research and some basic practices you can do or start today that will enhance your work. So data management covers how data is organized, backed up, and documented. Basically, can you or someone else find and use your data? Data management is a part of data sharing, which is increasingly visible because of concerns related to reproducibility and research transparency. So if the purpose of data sharing is to allow others to examine or build upon your work, it's really important that your data is managed in such a way that makes that actually possible. And if you're not sharing data publicly, you still don't want to lose it or lose track of it for your analyses. And research data management happens throughout this research lifecycle of a research project to guide the planning, collection, documentation, storage, sharing, and preservation of research data. And there's a very nice example of this research lifecycle shown on the slide. So to illustrate the importance of managing your data throughout a project, even after an article has been published, we are going to watch a short video. And this video was created by NYU Health Sciences Library to provide a comical look at what shouldn't happen, what should not happen when a researcher makes a data sharing request. All right, so it looks like I had a audio problem. So let's try that again to make sure that you can hear the video. We'll back up and try that again.
Hello. My name is Dr. Judy Benign. I'm an oncologist at NYU School of Medicine.
Hello, Dr. Judy Benign.
I read your article on B-cell function. I think that I could use the data for my work on pancreatic cancer.
I am not an oncologist.
I know, but I think I could use the data for my work on pancreatic cancer. Do you have the data?
Everything you need to know is in the article.
No. What I need is the data. Will you share your data?
I am not sure that will be possible.
But your work is in PubMed Central and was funded by NIH.
That is true.
And it was published in Science, which requires that you share your data.
I did publish in Science.
Then I am requesting your data. Can I have a copy of your data?
I am not sure where my data is.
But surely you saved your data.
I did. I saved it on a USB drive.
Where is the USB drive?
It is in a box. It is in a box at home. I just moved.
But can I use your data?
There are many boxes. So many boxes. I forgot to label the boxes.
Hello again. Thank you for sending me a copy of your data on a USB drive. I received the envelope yesterday.
You are welcome, but I will need that back when you are finished. That is my only copy.
I did have a question.
What is your question? You might find the answer in my article.
No. I received the data, but when I opened it up, it was in hexadecimal.
Yes, that is right.
I cannot read hexadecimal.
You asked for my data and I gave it to you. I have done what you asked.
But is there a way to read the hexadecimal?
You will need the program that created the hexadecimal file.
Yes, I will. What is the name of the program?
Cytosynth.
I do not know this program.
It was a very good program. The company that made the program went bankrupt in 2007.
Do you have a copy of the program?
I do not use this program anymore because the company that made it went bankrupt. Maybe you can buy a copy on eBay.
I have good news.
You again.
I talked to my colleague. She knew a person with a copy of the software.
Then why do you need me? Everything you need to know about the data is in the article.
I opened the data and I could not understand it.
If you have the program, you will find it is clear.
Well, I noticed that you called your data fields SAM. Is that an abbreviation?
Yes, it is an abbreviation of my co-author's name. His name is Samuel Lee. We call him Sam.
I see. And what is the content of the field called SAM1?
Ah yes, SAM1 is the level of CXCR4 expression.
And what is the content of the field called SAM2?
That is logical if you think about it.
What is the content of the field called SAM2?
I don't remember.
What about SAM3? Is there a guide to the data anywhere?
Yes, of course. It is the article that is published in Science.
The article does not tell me what the field names mean. Is there any record of what these field names mean?
Yes. My co-author knows what the content of SAM2 is, and SAM3. And SAM4.
Can I talk to your co-author?
I'm not sure.
I would very much like to talk to your co-author.
Well, he was a graduate student. He went back to China 2 years ago.
Can I have his contact information?
He is in China. His name is Sam Lee.
I think I cannot use your data.
You could check the article to see if what you need is there.
Please stop talking now.
Okay, so I really hope you enjoyed this cartoon. While it is quite funny, the situation happens quite often. And it really highlights some of the important areas of data management, including storage, documentation, and file formats. So some questions to think about from this video are, why did Dr. Panda give up on using the data? What made Dr. Spot's data unusable? And what things should he have done differently in this situation? So today we are going to use the checklist on the slide to guide our exploration of research data management. And this will help you set up and maintain robust data management practices and systems throughout the full life of a project. We will not go through all 24 of these items, but I will highlight a few to get you started. And sessions throughout this summer as part of our Great Data Cleanup will help you check off everything. And you can find this simple checklist of data management best practices on the Open Science Framework at the link on the slide. I've also put the short link into the chat. So the first step in our life cycle is to plan and design our RDM approach. And a useful tool that I want to point out is ORCID. And increasingly, research funders, employers, and publishers are asking us to sign up for an ORCID ID. An ORCID ID refers to a 16-character number that can be used to clearly identify you and not another researcher by a similar name. And an ORCID can be particularly useful for researchers who have published using several different variants of their name and initials, or have published under different names. And the whole idea behind ORCID identifiers is that they should be a stable link between all of your research activities. And it's free and very easy to sign up for an ORCID ID. You can add information about your research outputs and use your ORCID as a mini CV. And if you already have an ORCID, awesome. I suggest taking some time to maintain an active account. And as you publish your works, they will be automatically linked to your profile. Also in the planning phase, you should construct a data management plan or DMP for the project. And data management or data sharing plans are often required by funders, providing a brief description of how you will comply with those funder policies. And your data management plan should describe the types of data you will collect and analyze, collected data formats and final data set formats, how data will be organized and documented, active project storage and security, and data sharing agreements, including how and when the data will be made accessible to others. And additionally, roles and responsibilities for data management throughout the entire project. And DMP Tool is an online service to help you create a data management plan using templates from a variety of funders. And while you can check off creating a data management plan on our checklist, you should be sure to follow and modify the plan as you go through the project. So next is collect and create. And while in this stage you will be concerned with collecting and creating data, you also need to think about how that data will be named, organized, tracked, and documented. So file naming conventions are important to maximize access to your records. Ideally, you want to ensure your file names are descriptive and provide contextual information that allows the file to be identified outside of the folder where it is located. And here I have provided some quick best practices and examples of good file names. I'm not going into a lot of detail here, but overall you want file names to be descriptive, consistent, and appropriate length. So ideally around 32 characters is a good length for a file name. You shouldn't use special characters, periods, or spaces. Instead, use dashes or underscores. You should use leading zeros in sequential numbering to allow for multi-digit versions or reps. And don't be generic. You should really think critically about your file names. So instead of naming a file, mydata.csv, you should use a good descriptive name like having the date, the project name, and a rep number with that leading zero. And this is good. So the example in the last box of the table is good because the date is listed first and is in ISO 8601 standard, year, month, day. And the name contains some information about the file, and the file can then be sorted meaningfully. So files may be sorted by date or by the gene expression experiments, and then by the sequential repetition number. So one big note on file names, you don't want all of the metadata about your files in the file name. Most of this metadata will be captured in the form of a README file or in your lab notes. So additionally, one of the essential components of successful research data management is to establish a filing or directory structure for your records at the beginning of your project. And you should structure your folders, whether paper or electronic, to correspond to how data are generated and that complement your proposed or existing workflow. So established file plans demonstrate consistency and continuity in your record keeping. Ideally, you should arrange your data hierarchically, meaning folders within folders. So in order to create this folder structure, we identify ways we can divide our data into categories or attributes. And these attributes may be high-level projects based on time, data collection, location, or file type. And you should determine important contextual information about your files. To do this, think about how you would go about looking for a file. You should avoid overlapping categories, and don't let your folders get too big or your structure get too deep. So importantly, be consistent and document your system so that others can follow. Okay, moving along to analyzing and collaborating. So more and more research is a collective or collaborative effort of many individuals. And it often results from researchers who work together from different departments or across institutions. So therefore, when you are collaborating on a team, it is important to establish who will have access to what information and how that access will be provided. And obviously this can be enhanced with the use of digital tools and platforms. Creating a clear plan for file sharing will help you simplify the process and limit data risks and losing data. So use such things as collaborative file sharing platforms like Dropbox or electronic lab notebooks. And ELNs, electronic lab notebooks, help you share your research files with your group and have some nice advantages over paper systems, such as allowing you to enter protocols, observations, notes, and other data, maybe using your computer or even a mobile device. And ELNs are also searchable, shareable, and accessible from outside the lab. And a specific platform that I like is the Open Science Framework. And OSF is nice because it is cloud-based, providing project structure with a wiki for documentation, file versioning, and access controls. OSF also integrates with many additional platforms you may be using, like Dropbox, GitHub, or Google Drive. And as I mentioned, it is possible that members of a group will be using many different tools and platforms. So OSF is a great connector for everyone on the research team, no matter what platform they are using. So a key practice when analyzing your data is to always keep a copy of your raw data. Since analytical and data processing procedures improve or change over time, having access to that raw data can facilitate future analysis and that reproducibility. If only the derived data are stored, it can be quite difficult for others to confirm the results, to assess the validity of a statistical model, or to directly compare findings across studies. So therefore, we want to ensure that our data is always kept in raw format whenever possible. I suggest creating a folder for that raw data, maybe making the file read-only so that edits don't accidentally happen. And then you make a copy of that data to analyze. And the example on the slide shows how you would pull data into R and create your processing script for transforming the data in some way without modifying that original file. So next, towards the end of your project, you need to evaluate your data and determine what will be retained, shared, or destroyed. And two key practices that I just want to point out, but not discuss here, are to ensure you determine who owns the data and that data has been anonymized before you share it publicly. So here I'm going to talk about maximizing accessibility for the long-term value of your data. It's preferable to store data in formats that have freely available formats. And the appropriate file type will depend on the data being stored. So for example, numeric measurements, text, images, video, so on. And in most cases, when working with instruments to collect data, your data will be collected in these closed file formats. So as we saw in the video, the key idea for accessing data should not require any proprietary software, hardware, or have to purchase a commercial license. Proprietary formats change. Maintaining organizations go out of business, and changes in license fees may make access to data in these proprietary formats unaffordable and risky for end users. So in the best case, your data file should be both non-proprietary or open, and unencrypted and uncompressed. And the table on the slide shows examples of preferred open formats for data. So when you are preparing to publish or share your data, you should transform files to these preferred formats to allow for the most amount of access. So the last step you will come to in your research process is usually when you share or disseminate your work. So here I want to encourage you to think of sharing things other than research articles, but also any materials or methods you may have used. So for example, you may have run into situations where you have to spend time recreating reagents or sometimes use a misidentified tool. So additionally, labs have problems with reagent organization, validation, storage, and distribution. So reagent repositories like AdGene help solve these logistical problems by providing infrastructures to organize, document, and disseminate plasmids specifically. Additionally, research methods have a history of being mostly unuseful when published within research articles. You may have encountered a string of citations to follow or comments like methods followed standard procedures. So better practice is to think of a protocol as a brief, modular, and self-contained scientific publication. And protocols.io is a nice platform that supports the creation and sharing of research methods. You can include an abstract to put the methodology in context, include details like duration of steps and numbering of steps, safety information, and expected results. And these materials and method records can be attached and linked to your research articles in order to provide this full context of that project. So as I mentioned, data management is a part of data sharing. So we need some infrastructure to help support the sharing and discovery of long-term research data. And this is the role of repositories. You know, saying it's on my flash drive, just email me for a copy, or sending a USB drive in the mail is not a good choice. Even methods, you know, like posting data to a personal website or via Google Drive make it challenging to discover research data. So repositories provide this technical infrastructure for access, discovery, and curation of research data. They provide a persistent identifier and citation for your data. They provide a framework for you to describe your data using metadata standards. They archive your data in a trusted place for long-term access. And repositories are compliant with funder and journal requirements. And there are many types of repositories, so ensure you are picking the right platform for your work. Okay, the last section of our checklist we are going to go through is for storage and management of data. And this happens throughout the entire process. This is why we see the store and manage at the center of our lifecycle image. And the basic storage strategy I want to cover is the 3-2-1 rule. The 3-2-1 backup rule is an easy to remember acronym for a common approach to keeping your data safe in almost any failure scenario. So the rule is keep at least 3 copies of your data, store 2 backup copies on different storage media with one of them located off-site. So you should have 3 instances of your data that are here, near, and far. I say instances because you don't want to store multiple copies of the same file in the same place, because that would take up your valued storage space and also create confusion about which file to use. So let's look at 2 scenarios. So our first example, we have a lab computer. You would find a copy of the data here. Your near option is to also have a copy of the data on a portable external hard drive, which is stored off-site away from the lab. And your far option is installing Harvard Crash Plan on the lab computer, which will back up all files and is stored in the cloud. Our second example looks at what if you are working remotely, which we all are right now, mostly. You have a working copy on your laptop, and you are using Dropbox to sync your local files so that you could access the copy of your data if your laptop were to die or get stolen. And again, use Harvard Crash Plan to ensure your data is backed up and stored in the cloud. So notice how in this example, there is only one local copy of your data that is being backed up in 2 locations that you could retrieve if your data were something to happen to that local copy. So that concludes our walkthrough of our RDM checklist. As you can see, data management is complex and there are many steps involved, but I hope this will help you at least get started and set up some standards to move forward with. Again, here is the checklist that you can download from the Open Science Framework project. So in review, research data management covers how data is organized, backed up, and documented. Data management is for all projects. Even if you're not sharing data publicly, you still don't want to lose track of it or lose track of your analyses. RDM is a collaborative effort across the entire research lifecycle, and there are many groups invested and provide support for all aspects of data management. And as I just mentioned, data management is complex. There are many different types of stuff to keep track of and many different software and platforms to navigate. And it must happen while you do your research. So it's important to delegate responsibilities, seek resources, and identify streamlined workflows to help you. Again, this website is a great resource of all the topics we covered today, and you can find the webinar recordings and submit questions as you start your data management journey. Remember, we have a full lineup of webinars every week this summer. Next week, we will break down some of the data management terminology that we went through today. So thank you very much for joining. The recording and the slides will be posted on our website. We will also send out an email when these are available. And I would appreciate your feedback on today's session. So please fill out the survey at the link provided.